Hello everyone. In this video, we are going to see the solution of GATE Aerospace 2022 questions, and the topic that are related to the questions are flight mechanics and space mechanics. So space mechanics, they have asked only one question this time, so that is also incorporated in this video. Uh, Along with that, the aircraft performance plus aircraft stability both will come under the flight mechanics part. So that solution will also be available. So let's start with the first question. So the question here, what is asked in this question is the service ceiling of an airplane is. So it's a very easy question. Basically, they're just asking the definition of service ceiling. So there are n number of ceilings in the aircraft, right? One is like service ceiling, the other is like absolute ceiling, the other is like propulsion ceiling, design ceiling, like different ceilings are available. So the most common ones are absolute ceiling and service ceiling. So the definition of service ceiling is an altitude at which the aircraft's maximum rate of climb will be 100 feet per minute. Okay, it is given 100 meter per minute, so don't jump into that. So actually 100 feet per minute. So option D is the right answer. Okay, that's the definition of service ceiling. Basically, the altitude at which the aircraft's maximum rate of climb will be 100 feet per minute, because as you all know, as altitude increases, the rate of climb will decrease, right? So altitude and rate of climb is inversely proportional, right? As altitude increases, the rate of climb will decrease. So definition of service ceiling is the maximum rate of climb is 100 feet per minute. So beyond which theoretically the aircraft cannot sustain. All these things is applicable for absolute ceiling, not for service ceiling. So the option is D. Regarding the horizontal tail of the conventional airplane, which one of the following statement is true? So first of all, regarding the horizontal tail of the conventional airplane means if an aircraft is like this, right? So there will be wings here and the tail will be here, right? The tail will be here. So in conventional aircraft, the tail will always be at the rear. I mean, after the wing, right? But for certain military aircraft, certain configuration, canard and all, the tail will be above the or before the wing. But in this case, the tail will be after the wing. That's how the general conventional aircraft is. So what they are asking is which of the following statement is right. So Cm alpha, which is like moment quotient due to the angle of attack, right? So Cm alpha is nothing but, so we know that Cm suffix alpha, so which is dCm by d alpha is equal to minus eta t. This is tail efficiency. VH is tail volume ratio. Then AT, which is the lift curve solution of the tail, lift curve coefficient of the tail, slope of the tail, 1 minus d epsilon by d alpha. So this is the dCm by d alpha, which is Cm alpha equation. So this is the contribution the tail is providing for dCm by d alpha, and it is very clear that where eta t is the tail efficiency, VH is the total volume ratio, AT is equal to tail lift curve slope, and E is downwards due to the flow over the main wing. So E is nothing but downwards due to the flow over the main wing. So if you see here, right, for any conventional airplane, Cm alpha from this equation, because this is the tail contributing equation, it is very clear that Cm alpha is negative, right? It is very clear that Cm alpha is negative, which only gives the stability effect, right? It has to be negative so that only it can give the stability effect. So option A is the right answer. It contributes to the Cm alpha less than 0, because it has to be less than 0, so that only it can be negative, right? So that's the reason. Option A is the right answer. Okay. Now in this question, for international standard atmosphere up to 11 kilometers, so they are meaning only for troposphere, right? Up to 11 kilometers only troposphere, right? Which of the following statement is or true? The hydrostatic and aerostatic equation is used. B is the total the temperature lapse rate is taken as minus 0. -2 Kelvin per meter. And then C is they have given the standard sea level condition, atmospheric conditions. D, the air is treated as perfect gas. Out of these, which are the following statements are true? So first of all, only the temperature equation, right? T is equal to T naught minus AH, where A is the lapse rate. And lapse rate, we all know it is 0.0065 meter per, sorry, Kelvin per meter, right? So this is kind of very straightforward. The lapse rate is 0.0065, so option B is wrong, right? So option B is very clearly wrong. Here they have given a different lapse rate. Yeah, and it will be negative as well. Yes. So now, using this temperature relationship, we also derived the pressure variation and the density variation along the altitude, right? In the flight mechanics. To derive the pressure variation and density variation along the altitude, we have used hydrostatic equation, right? So dP is equal to minus rho g h. So this is what is hydrostatic equation, and we started with this hydrostatic equation, and basically we converted this into aerostatic equation by using our ideal gas equation. What is perfect gas equation? P is equal to rho RT. So this is what your perfect gas equation. We have, instead of rho, we substitute P by RT, then only we found the relationship between the pressure and the altitude. Similarly, then we did it for density and altitude. So we have used hydrostatic equation, that is true. Similarly, we have also used air, or we have treated air to be perfect gas. That's why we have used this ideal gas equation also in deriving the relationship between the pressure and altitude and density and altitude. Because for temperature it is a measured equation, whereas the pressure and variation with respect to altitude and density variation with respect to altitude are derived equations. So for that we have used, in that derivation we have used this P is equal to rho RT, which means that we have assumed the air to be perfect gas or ideal gas. So option D is also right. Option C is wrong because density and pressure at sea level condition values are same. It is 1.01 bar and 1.225. Whereas temperature is actually 288 Kelvin, right? 15 degrees Celsius is the sea level standard condition. But whereas here it is given 300 Kelvin. So actually it is 288 Kelvin. That's the reason C is wrong. So option answer is option A and D. Okay. Okay. This is very easy question. An unpowered glider is flying at a glide angle of 10 degrees, right? Its lift to drag ratio is. So we all know the relationship between the glider and the lift to drag ratio, right? So tan glide angle, if the glide angle is theta, tan theta is equal to drag by lift, right? So this is, if you draw the force balance of the gliding aircraft, we will come to know that. See, this is the gliding aircraft. Yes, if the aircraft is coming like this, so this is tan theta is equal to d by L, and then from tan theta is equal to d by L, theta is given tan 10 degrees equal to d by L, and they want lift to drag ratio. So L by D is equal to 1 by tan 10 degrees, and if you substitute that, you will get your L by D to be 5.73, close to that value. Okay, 1 by tan 10 degrees is equal to 5.73. So the answer will be lift to drag ratio is 5.73. Moving on to the next question. It's also very easy question. It does not have a lot of performance inside it. Actually, it's kind of a mathematical question only, because what is asked in the question, consider a conventional subsonic fixed wing aircraft. E is the Oswald efficiency factor and AR is the aspect ratio. Good. Corresponding to the minimum CD by CL3 by 2, which of the following relationship is true? First of all, as soon as you see this, we know this corresponding to minimum CD by CL3 by 2 is nothing but CL power 3 by 2 by CD max condition, right? See, if you take the inverse CD by CL 3 by 2, if it is minimum, then this is the max condition, right? So this max condition is nothing but power minimum condition. We all know that, right? If it's CL by CD max, then it is drag minimum. CL power 3 by 2 by CD max is power minimum condition. We all know that in power minimum condition, we have already derived that. We don't need to drive it here in the exam hall. CD naught, your profile drag coefficient, is equal to CDI by 3, right? Your profile drag coefficient is nothing but CDI by 3. Using this relationship, we will do some mathematical manipulations here so that we will derive any of the results that is given in the option, right? But now you see the option, nowhere it is given CD naught. Everything is in terms of CD and CL. So we all know CDI, which is induced drag coefficient, is equal to nothing but KCL square, where K is nothing but 1 by pi EAR into CL square, right? The value of K is 1 by pi EAR into CL square. So if you see the option, pi EAR, everything is available. CL is also available. Instead of CD naught, it is given in terms of CD. That's it, the total drag coefficient. By drag polar, we all know that the total drag CD is equal to CD naught plus K CL square. With the condition that is given in the question, which is the max minimum power condition, we know that CD naught is equal to CDI by 3, right? With this, what we can do is, in this equation, instead of the CD naught, we can substitute CD naught in terms of CD and KCL square. So this equation drag polar will tell you CD naught is equal to CD minus KCL square. So now let's substitute that here. Instead of CD naught, we'll substitute CD minus K CL square, which is equal to 3 CDI by 3. Now CD is equal to CDI by 3 plus K CL square. Again, CDI is also nothing but KCL square, right? So KCL square by 3 plus KCL square. So you will get something like 4 KCL square divided by 3 equal to CD. Right? Now CD by CL square, you take the CL this side, is equal to 4. What is K? 1 by pi EAR, right? By 3 pi EAR. If you see the option B is the right answer, right? CD by CL square is equal to 4 by 3 pi EAR. That's what we also got. So option B is the right answer. You have to just know what is the relationship between your profile drag coefficient and induced drag coefficient during this power minimum condition. That's it. From there, we have to just do some mathematical manipulation and jugglery to reach this results. That's it. So option B is the right answer. Moving ahead, this question is relatively a straightforward question. So for a conventional airplane in straight and level constant velocity flight condition, which of the following conditions are possible on a Euler angles? Angle of attack alpha and the side slip angle beta. Okay, so it is clear that for the velocity to be horizontal, you all know, right? Your theta has to be equal to alpha. Hence, only your velocity will be horizontal, because alpha is nothing but angle of attack, the angle between the chord line and the free stream velocity, whereas theta is the angle between the horizontal level and the chord line. So if you want your velocity to be horizontal, then obviously theta has to be alpha. That is the first inference that we can make. The second thing is, for a straight flight, there should be no side slope angle, because it is clearly given that the flight is a straight level flight, right? So there should be no slight slope angle. So beta has to be 0, right? Beta has to be 0, right? Yes. And then if beta is equal to 0, we all know that beta is equal to minus psi. So if since beta is equal to 0, which implies that your psi is equal to 0. So now you have got three things, right? Alpha should be equal to theta. Beta has to 0 because of no side slips, because it's a straight flight. Psi will also be 0 because beta is equal to minus psi. If you see, all these things are satisfied in option A. Theta is equal to 2, and hence angle of attack is also 2. So theta and alpha are same value. Psi and beta are. So this is only getting satisfied in option A. That's why the answer is option A. Okay. So this is a relatively very easy problem. They have asked the question about the tan. A conventional airplane of mass 500 kg is doing a level turn of radius 1000 meter at a constant speed of 100 meter per second at sea level. So the aircraft is taking a level turn where they have taken the V infinity is equal to 100 meter per second, and the weight of the aircraft is given to be 500 kg, 5000 kg, sorry. Radius of the turn R is equal to 1000 meters. So the radius of the turn is 1000 meter. So they are asked us to assume 10 is, acceleration due to gravity to be 10 meters square per second. The bank angle of the airplane to achieve this radius of turn of an aircraft which is having this much weight, which is taking a turn at a constant speed of 100 meter per second, what would be the bank angle of the aircraft? So the relationship between the radius of turn, which is R, is equal to V square divided by G into root of n square minus 1, where n is nothing but your load factor. Load factor, which is equal to L by W. In tan, your L by W is nothing but sec phi, where phi is the bank angle. So n is equal to sec phi, secant of phi, where phi is your bank angle. That is what is asked in the question. So now let's figure out n. From that we can get the bank angle. So R is equal to 1000, which is equal to V square, which is V infinity square, which is 100 into 100 divided by 10, which is acceleration due to gravity, n square minus 1. So if you do that, you will lose this. So this will go, and this is again 1000, so entire thing will go. So finally what will you get? This will implies n square minus 1 root is equal to 1. So now if you take a square on both the sides, n square minus 1 is equal to 1, then n square will be 2, and this will tell you n is equal to root 2. Right? Now you have got your load factor n to be root 2, but the question what they have asked is the bank angle. So now the relationship between load factor and the sec phi, right? So load factor you have found out root 2. Sec phi is nothing but 1 by cos phi. So cos phi is equal to 1 by root 2. So phi is nothing but cos inverse of 1 by root 2, which is 45 degrees. So the bank angle at which the aircraft is making a turn of radius 1000 meter and at a constant speed of 100 meter per second is 45 degrees. Okay. Okay. And the next question is, it's from space mechanics. We will see that question also in this thing. So consider a high Earth orbiting satellite of angular momentum per unit mass is h vector and the eccentricity is c. So they have given what is the angular momentum. The angular momentum is denoted as h vector. Okay, and eccentricity is E. Okay, good. The Earth, the mass of the Earth is m, and G is the mass of the Earth is m, and G is the universal gravitational constant. So that everybody knows. Good. The distance between the satellite center of mass and the Earth's center of mass is r. So the satellite center of mass and the Earth center of mass, the distance is r. The true anomaly is theta, and the phase angle is 0. They are given the phase angle is also 0. Which of the following statement is or true? So it can be multiple statements can also be true. So to solve this, right, let's take the governing equation, right? The governing equation of a two body problem. So it's a two body problem, right? The Earth is also revolving and the satellite is also revolving. So it's a two body problem. Let's take the governing equations of the two body problem. So this is how the governing equation, which is equal to minus mu divided by r cube into r vector, where we know mu is equal to g into m, which is nothing but your constant g into m, mass of the Earth, right? The the same equation can be represented in the scalar form, right? This equation in scalar form can be written as conservation of energy, right? The same equation in scalar form is nothing but conservation of energy. And also the same equation is nothing but conservation of angular momentum as well, right? So it is a conservation of energy and this is a conservation of angular momentum. If you go back, H vector is nothing but conservation of angular momentum, so that is correct. The sum of potential energy and kinetic energy of the satellite is conserved, so that is also right because it's a conservation of energy equation, right? So conservation of total energy is conserved, angular momentum is conserved, both of them are true. Now out of option A and B, what is the trajectory equation you have to find? So the trajectory equation formula we all know, R is equal to, trajectory equation is nothing but solution for this equation, P by 1 plus E cos theta, which is equal to, P is nothing but H square by mu divided by Gm into 1 plus E cos theta, where E is eccentricity. So which is equal to H square, sorry, I'm writing P square is equal, P is equal to H square by Gm. Okay, Gm is nothing but mu divided by Gm into 1 plus E cos theta. So this is what your trajectory, which is the solution for this equation. So if you go here, it is very clear. Option B, right? It's very clear. The difference between option A and B are only the square. So we all know that. So option B is the right answer. So B, C, D, all of them are correct. So answer is B, C, D. All of them are right. Okay. With this, the solution of the flight mechanics as well as the space mechanics of GATE Aerospace 2022 questions are done. Let me know your suggestions in the comment section. Thank you.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.